Today we will be classifying functions in lesson 2.3.b. We will first look at what is a function, and then we will be able to recognize the difference between both linear and nonlinear functions, as well as determine an appropriate rule that would represent a nonlinear function. So let's ask some key questions first. What is a function? A function is a relationship. So if you think of a function, it is a pairing between each input value with exactly one output value, so an x and a y. What is a linear function? A linear function is a function whose graph is a non-vertical line. So we have this line here, we even can represent a dotted line, or we can even have a horizontal line. But as you'll see in the next lesson when we cover slope, a vertical line is not actually considered a linear function. Okay, but the key thing behind what is a linear function is that it is a line. So then what is a nonlinear function? And that is a function whose graph is not a line. Here's some examples. This first one actually represents a quadratic equation, an equation that has an exponent. This second one is a cubic function, and the exponent on this one is a 3. And this last one, which we will be doing shortly, is an absolute value equation. These are all nonlinear functions, but they are in fact functions because they have a pairing. Every x value has exactly one y value. So let's look at some examples. In this case, we're looking at pizza area and the sauce cost. The area A, and here's our A to represent area, in square inches of a pizza is a function of its radius r. Okay, so our area, what they're saying is that the area is determined by how big the radius is of the pizza, and r is in inches. And if we look at this second graph, the cost C in dollars of the sauce for a pizza is a function of the weight, which is W, in ounces of sauce used. So the more sauce that's used, the greater the cost. So it says graph these functions shown by the tables below, and then is each function linear or nonlinear? Let's first look at the graphs. This first graph forms a curved line, and as we just learned, that is not a linear graph. This graph is a curve, not a line, so the function is non-linear. Our second graph, this graph is a line, so the function is linear here. So visually, it's very easy to tell if you have a linear equation by looking at your graph. Okay, and then we have some extra notes in here. The vertical axis right here represents the independent variable, the dependent variable, and the x-axis represents the independent variable. And remember that we said that our area depends upon our radius. So our radius we choose, and then our area is affected by the radius. In the second example, our cost is our dependent variable because it depends on how much sauce we use. The more sauce we use, the greater the cost. So our sauce is our independent variable. Now another way to determine if an equation is a linear or nonlinear function is to look at the tables. If we look at these two tables, let's first look at our independent variable here, or we called that x in the past. We are going up by a consistent amount, 2, 4, 6, 8, 10. We are going up by 2 every time. Same thing with the one on the left. So as long as the one on the right is going up by a consistent amount, we would have a linear equation. And if we examine this one on the right, well, this one goes up by 80 cents. The second part goes up by 80 cents. And it looks like it continues on that way all the way down the table. Since it's going up by a consistent, constant amount, and our x value, or our weight, our independent variable, is also going up by a constant amount, this would be a linear equation, as we can see from the graph. On the other hand, on this one, the one on the left, $12.57, if we take away that from 50, we get 38, or not dollars, sorry, that we're looking at area on this one, dollars on the other one. And then if we take the difference here between 50 and 113, we may need our calculator. All right, we've got our calculator. Let's plug that in. $113, sorry, 113 square inches, 113.10 that is, minus 50.27 gives us 62.83. So right now we already have a difference, 62.83, so we are not going up by a constant amount. I could continue to check my differences if I tried this next one, 201.06 square inches minus 113.10 square inches. I get a difference of 87. So again, I'm going upwards, but not at a constant rate. Therefore, the graph looks like this down here. And you can see, in fact, it is not a linear graph. It is curved. Okay, let's move on to the next example. This table shows the fraction A of a piece of paper, an original piece of paper that remains after the paper has been cut in half n times. So we cut the paper in half the first time, half the paper is remaining. Then if we take that half and cut it in half again, we now have a fourth of the paper remaining, and so on and so forth. So what we want to determine is if this function is linear or nonlinear. Well, if we look at this top value, this would be our independent variable, or x, and as they call it in this problem, n. We increase by a constant amount every time by 1. So not a problem there. Let's look down here. We are decreasing, let's move this down actually, we are decreasing by a certain amount each time. Let's figure out what that is. Okay, if you are good with fractions, you may be able to do this in your head. If not, I would suggest getting a common denominator. Well, these are all of these are, will go into 16 actually. 16 is divisible by all these. So let's make 16 be our common denominator. If we change this to 16, we would need to multiply 2 by 8, which means we need to also multiply the 1 by 8. So we would get 8 over 16 for our first one. 4 goes into 16 4 times, so we would multiply the 1 by 4 and get 4 over 16 for the second one. 8 goes into 16 2 times, so we would end up with 2 over 16 for the last one, or the third one I should say, and then 1 over 16 for the last one. Now it will be easy to see the decrease each time that we cut our paper. 8 minus 4 is 4, so this goes down by 4/16, but let's go ahead and reduce it. And that gives us 1/4. So we drop down 1/4, from 1/2 to 1/4. Let's look at our second decrease. We go from 4 to 2, which is 2/16. And again, let's reduce that, and we end up with 1/8. So we do not have a constant amount. And let's do our final one. 2 minus 1 is 1. That leaves us with 1 over 16. So the change from the first point to the second was 1/4. The change from this one, the second one to the third one was 1/8. And the change from the third one to the last one was 1/16. This is not a constant rate of change. So in this case, we would have a non-linear function. All right, let's look at how we might write a rule to represent a nonlinear pattern. I'm briefly just going to go over this, and then as we move forward, I will be giving you rules, and you will need to understand how to test each rule to determine if it's the right rule for the pattern. So here is an example of a table where we have on the x-axis 1, 2, 3, 4, 5, so a constant rate of change here. And then on the y-axis, though, look at this difference. So we go from 2 to 4, that's a difference of 2. We go from 4 to 8, that's a difference of 4. 8 to 16 is a difference of 8, and 16 to 32, a difference of 16. So it's definitely nonlinear. Well, the way I look at this is we start with the first coordinate point, 1, 2, and we figure out what rule could produce a 2 given an x value of 1. And we can write them out. So I wrote out y equals 2x. That works, right? If you plug a 1 in for x, y would equal 2, which it does. You also get y equals x plus 1. That would work. If I plugged in a 1 for x, 1 plus 1 is 2, and that works as well. And then finally, here's an exponential rule, and we haven't really talked about exponents yet, but let's look at this. 2 to some power, y equals 2 to some power. So if I plug in a 1 for x, 2 to the first power is in fact 2, and that works as well. So I found 3 rules that work for my first point. The key then is to test them in your second point and see which ones work. Let's look at our first rule here, or this rule, y equals x plus 1. If we plug in a 2 for x, we get 2 plus 1 is 3. That does not work. So we can cross that rule out as ineffective. It would not work. Let's cross that one out. Let's look at the second one, y equals 2x. Well, if we plug a 2 in, 2 times 2 is 4, so that works great. Now let's look at, let's look at the next point down and see if it works for that. So if we plug a 3 in for x, 2 times 3 is 6, but we need it to equal 8, so this rule no longer works. Now let's try our last rule that we came up with, y equals 2 to the x. Well, if we know it works for the first one because that's where we came up with it, so let's look at the second point. If I plug a 2 in for x, 2 squared, meaning 2 times 2 is 4, and that works. Let's go ahead and try it for the third point. 2 to the third power means 2 times 2 times 2, which gives us 8, and that works. Let's just double check with a 4. So 2 to the fourth power is 2 times 2 times 2 times 2, which is in fact 16, and it works for that as well. So the rule that represents this table would then be 2 to the x. Okay, let's try a couple more. Which rule represents this pattern? So here we have some ordered pairs, and we just need to figure out which of these rules works. Well, the way we go about it is we just test them. So let's test our first point, 1, 1. Well, if I plug a 1 in for x, y will equal 1. So that actually works for that point. Let's try the second point. If I plug the 2, which is my x value, in for x, well, y would then equal 2, so that rule does not work. We can cross that rule out. Let's check the second rule and make sure that works. Okay, so let's plug a 1 in for x. So we would have 1 squared, which is equal to 1. So that works. Let's try our second point. In our second point, we have, change colors, we have a 2 for x, so let's plug in a 2 and square it. And 2 squared is equal to 4, so that works. Let's try one more point just to make sure. Let's try this one, the 3, 9. So let's plug a 3 in for x, and we will go with 3 squared there. 3 squared is 9, so that works as well. 9 equals 9. So it looks like we have proven that the second rule is a solution, and that is the rule that represents this problem. Okay, let's try this last one. We have these ordered pairs. Which of these rules is going to work? Now remember, once it doesn't work for one of the points, we can scratch it off. It won't work. All right, let's try this first one. So if we plug in a 0 for x, we get a 0 for y, which works. But if we plug in a 4 for x, we still get a 4 for y, so that wouldn't work for that point. So let's cross this one off. This one does not work. Let's try our second rule. If we plug a 0 in for x, well, 0 minus 1 is -1, and that one doesn't work. So I only had to test the first point on that one. Let's look at our second rule, or our third rule here. If I take a 0 and plug it in, well, 0 squared is in fact 0, so that works. Let's try the next point. Let's plug in a 1 for x. 1 squared is 1, not 4, so this one doesn't work. It looks like this last rule is probably going to be my answer, but let's just make sure. We need to test it. We'll try 0. So let's plug in a 0. So y equals 4 times 0 squared. Well, 0 squared is just 0, and 0 times 4 is 0, so y would equal 0, which is what it does. So we're good with the first point. Let's try another point. Let's try our second point. In the second point, we have y equals 4 times 1 squared. Well, 1 squared is just 1, and 1 times 4 is 4, and that's what we need it to equal. So that one works. But let's go ahead and make sure. Let's try a third point. If we can get a third point to work, then most likely we have found our rule. Okay, our third point is 2 comma 16. So let's plug in a 2 for x. 2 squared, remember, do your exponents first. 2 squared is 4, and 4 times 4 is going to be 16, and that does in fact work. So it looks like we have found and proven that y equals 4x squared is in fact the correct rule. And that concludes our lesson for today. We'll see you at the next lesson.